Hi, welcome back to another video. Today we're going to be talking about electron configuration. For some of you, this is going to be review, and for others, this is going to be completely new. But our main target is to write electron configuration, so I'm going to go over shells, subshells, orbitals, and electron spin. Some quick review: Rutherford and Bohr models of the atom. Rutherford's model is sometimes called the planetary model. It's where there's a dense, positively charged nucleus at the center, surrounded by negative electrons. A reminder that he discovered that positive, dense nucleus using the gold foil experiment. But essentially, his whole model is based around the attraction between these oppositely charged particles. That attraction is governed by what's called Coulomb's law, which in this box right here, you can see that the force, so the force of attraction or repulsion, is related to Q1, Q2 over R squared. Q represents the signs of our particles, and R is the amount of space between. So Q, for example, can represent a proton, Q2 would represent an electron, and R squared is the amount of space in between those two particles. If our particles have the same sign, they're going to be repulsed, so the force would be repulsive. If they have different signs, opposites attract, and we're talking about an attractive force. If you've ever rubbed a balloon on your head and then created static and stuck it to the wall, it is that same attraction between particles governed by Coulomb's law. If you've taken physics or plan to take physics next year, you'll talk more in depth about this. So continuing, Bohr adopted Rutherford's model, but he made a few tweaks to it. First, he suggested that electrons could only travel in fixed orbitals or shells around the nucleus. The term we use nowadays is shells. He used a spectroscope with gaseous elements and found that they emitted a certain amount of electromagnetic radiation. The light was emitted in discrete packets of energy called quanta, and each element emitted a unique radiation pattern. So if you think back to last year or 2 years ago when you took Regents, we discussed atomic spectra, which is where electrons are excited, and when they fall back and release energy, they release light, or quanta, making a spectra, which is also called the fingerprint of an element. As I was just saying, electrons gain energy, then release energy as they fall back to their original state. The lowest energy state possible is the ground state, and the highest energy state possible is the excited state. An electron can also gain sufficient energy and be completely overcome. What that means is an ion is formed, so with enough energy, an electron can be completely ripped away from an atom. The specific amount of energy needed to remove an electron is called ionization energy. It's called first ionization energy if you're removing one electron, second ionization energy if you're removing a second electron, so on and so forth. Bohr still didn't have everything quite right. One of the limitations of his model is he ignores the fact that electrons are a particle, which means they have both the characteristics of a particle, which is how he treats it, but also a wave-like property. So in comes Schrödinger, who predicted a three-dimensional probability for the location of electrons. So this is the electron cloud model, and the model that we currently use. He predicted that the maximum number of electrons in each shell is given by 2n squared, where n is the shell number. And here you can predict how many electrons will be in each shell. Note that the shell number corresponds to the period number on your periodic table. So, period number 1 can only hold a maximum number of 2 electrons. 2n squared is 8, so on and so forth. Each shell is then further divided into subshells. The number of subshells in any given shell is equal to the shell number. So for example, shell number 3 is going to have 3 subshells. The first subshell in any shell is the S subshell. The second is the P subshell. The third is the D subshell, and the fourth is the F subshell. And here's a chart describing the subshells in each of our shells. So for example, in shell number 1, there's only going to be one subshell, and that's S. In 2, there can be 2 subshells, that's S and P. It does go beyond S, P, D, and F, but we will not be covering that in AP chemistry. So the Pauli exclusion principle states that all electrons in an atom must be unique. So when we're talking about electrons that are in the same orbital, meaning they're in the same shell, the same subshell, and now the same orbital, they've been assigned an intrinsic property known as spin. When we're drawing, which we'll practice later on this week, 2 electrons in the same orbital will be assigned different or opposite spins. This is denoted with a half arrow pointing up and the other half arrow pointing down. It can also be denoted with quantum numbers, which would be plus half and minus half. And again, this is just to distinguish between the 2 electrons in this orbital. Here's a useful chart that just summarizes everything I just discussed. So if you would like to copy this into your notes, feel free. All right, rules for filling orbitals, also known as Aufbau process. First, figure out how many electrons are present. So if we're talking about an atom, atoms are neutral, so it's going to equal the number of protons for that element. If you have an ion, you're going to have to add and subtract electrons accordingly. Always fill the lowest energy orbitals first. 1s has a smaller amount of energy than 2s, so on and so forth. A little more on this on the next slide. And then there's also Hund's rule of maximum multiplicity states, which has to do with if there's more than one orbital with the same amount of energy. These are called degenerate orbitals. Then one electron is placed into each orbital before pairing occurs. So for example, in the P subshell, there's 3 orbitals. All of the orbitals in that P subshell are degenerate, meaning they have about the same amount of energy, and you would fill 1 electron into each of those orbitals before pairing. And as I was just saying, all orbitals in the same subshell will have a similar amount of energy. Here's your filling order. So it's based on the periodic table. You should be able to look at the periodic table and fill accordingly. In the first period, we start with 1s, we head to 2s, 2p, 3s, 3p, 4s, 3d, and this is the order we fill in. This is known as the p block, the s block, the d block, and the f block. And we're going to practice filling together. A little bit on the notation we're going to use. So we're going to write the period number, which is equivalent to the shell number. Note that when filling the d orbitals, you have to subtract 1 from the period in order to determine the correct shell number. Add 1 electron for each element unit until the orbital, the subshell, and then ultimately the shell is filled completely. Then record the electronic configuration in the following format. It should be shell number, or the period that's on the periodic table, orbital, so S, P, D, or F, and then the number of electrons in that orbital as a subscript. For example, Helium has 2 electrons found in the first shell in the s orbital, and it would have the electron configuration 1s2. And once again, the 1 is the shell, s for orbital, 2 for the number of electrons inside of that orbital, and this is pronounced 1s2. Alright, so we're going to do a couple practice problems together. So first we're going to look at fluorine, which has 9 electrons. Normally what I would do is go to my periodic table, look up fluorine. I see that it has 9 protons, therefore I know it has 9 electrons. But for the sake of the rest of this video, I'm just going to fill out the electron configuration. So if we take a look, we're going to start in the 1s. Alright, I've reconfigured this just so I can better show you what I'm doing. But anyway, fluorine has 9 electrons, so I'm going to start in the 1s. And I have 2 electrons in the 1s. I move on to my second period, or my second shell. I'm still in the s block, and I have 2 electrons again. I now entered the 2p block. So I'm still in energy level number 2. I'm now in the p block, and I have 1, 2, 3, 4, 5 electrons. Now I'm going to check my work really quick. I have 5, 6, 7, 8, 9 electrons in total. Let's do that again with phosphorus. So once again, I'm going to start at the top. I'm in the first energy level. I'm starting in the s block, and there is 2 electrons. I head into the second energy level, the s block, and there's 2 electrons. I now entered the 2p, and there's 1, 2, 3, 4, 5, 6 electrons. I enter 3s. There's 2 electrons. And I now enter 3p, and there is 1, 2, 3 electrons in the p orbital. I'm going to check my work. 3 plus 2 is 5, plus 6 is 11, 12, 13, 14, 15. I again have all of my electrons. And last but certainly not least, I'm going to do aka antimony. Well, let's take a look. I start at 1s again. So 1s2, 2s2, 2p6, 3s2 is filled, 3p all 6 filled. I now enter 4s2. This, remember, when we entered the D block, is actually 1 less than the period, so that's 3d10. Then 4p, my bad, 4p6. Then we enter 5, 4d10, all the way until we get to 1, 2, 3, 4. 5, 1, 2, 3. And once again, if I add up all of these electrons, it's going to add up to 51. We're going to practice this in class tomorrow, and we're also going to talk about orbital diagrams. If you have any questions, please let me know. Otherwise, have a good night.